And welcome back for one more episode of Python Plus. I have been waiting for such a long time doing this episode. Unfortunately, I've been working quite hard on some projects, and of course on my PhD. So sometimes you're just busy, but I think it doesn't really matter. That's life, the way it is. I'm Cody, I'm your host, and today I will show you a really neat technique which I've just recently used, and I think it might benefit many people seeing this. Now, what we want to do is we want to map results between meshes. Oh, why is this red? I don't know. But let's stick to red because red is a nice color. And what I'm actually talking about, just imagine you have this mesh here, which would be terrible because it looks very, very bad. But just imagine it that we have this mesh and we want to kind of translate results because the meshes might be incompatible. And yeah, what we kind of have is we have these two meshes. Let's call them MR1 and M2. I really need to work on my drawing. I need to get a drawing pad, not use the mouse. And what we have is at the centers of the elements we have the kind of the data, the element data is saved onto the centers. And the problem is when you want to compare different meshes, that let's take a different color. If you translate the results over here, it's hard to compare because this one would be here in this blue spot, and of course these two are way off. So it's not like you can extract all the data from this mesh and from this mesh and simply subtract them or something like that, because the matrices representing these two data meshes usually are not of uniform shape. And what we want to do is today, let's refresh this one here, is just think of it that way. We have a mesh. Let's keep it easy, like this. And let's say we have a second mesh, which I will not draw strongly. I don't know. Maybe I will. Okay, so let's say we have the next center from the mesh 2 is here. Okay, and what we want to do is we want to kind of map all the results onto mesh 2. So we take the results and compute something like a distance weighted mean. Okay, so what you literally do is you take neighbors. Oh no, not, oh no, how terrible. Let me just quickly redraw this. You take the neighbors, and the task itself is simply very easy. We need to compute the 4 closest neighbors, and then we simply apply distant weights. Okay, so what we have in the end here, let's say this is some value, and if we want to compute the mapping, we say, okay, our new I don't know, our new value is just a sum over some neighbors. Let's say 4 here. You have to specify it usually. And what you simply do is you multiply it with some distance weight times the element data, which you have here, here, or here, or here. Okay, so this looks rather fancy because you have to do this for all of the V's of the other mesh, like all of the element centers. But to be honest, when I programmed this one here, I was very surprised that I needed only 5 lines of code in Python to perform this mapping operation. And I want to show you this because this is one of the things you want to show off in Python, is you can do these amazing things quite fast. So we will need NumPy, and of course we will also need my d3plot library. If you don't know it, it's just for reading LSDyno result files And of course, this is a library or a module in my library which is not for outsiders usually, but I'm thinking about releasing a few functions from it because, of course, they're quite convenient. So first, we need to specify what we want to compare. Let's go with, I don't know, plastic strain, simply because I use it mostly. Doesn't really matter. And also we need an element evaluation function, which is kind of which result do we wanna use. So let's take the result. Yeah, let's take the plastic strain, and I will just insert this test here because some element types or rigid elements, yeah, they do not have some result data. Sometimes this is just empty. So we need to check if there's something inside, and if something is inside, we take it from the last time step. Otherwise, we'd simply return 0. So it's nothing special, and this is all we need to set up. Okay, these are kind of like the settings. We can exchange them later on quite easily. So let's do the thing. Here we go. Let's load 2 different D3 plots. I have 2 different in the folder, so don't be curious where I get them from. By the way, they're compressed, so I need to decompress it. And yeah, I need to, of course, read the results directly. And we simply do the same for the second file here. Okay, so now we have the 2 files which we want to do the mapping in between in the memory. And now comes this magic function which I've programmed in my library. And I use it for exactly the purpose I show you. I think it's, yeah, let's call it FEM-Data 1 or results. Let's call it FEM-Data. And what this function does is it extracts the element centers and also some results if you wanted to. The name is pretty confusing because it says just extract element coordinates. So if I ever release this function, I of course will rename it. But as you can see, I was very oh man, so confusing. I did some good documentation on it. So fortunately I can look it up now because I have no clue what I did at that time. It's quite some time ago. So here we go. And the second one is this function here, and this should be already enough. Let's call the argument explicitly. So we get all the parts from the D3 plot and then apply the result function on it. And of course we need to do the same thing on the second file as well. And I want to show you one thing here. Here we go. I want to show you that these 2 meshes are different. So let's take just the element centers and get the shape and maybe also the data, because I want to show you what the matrices are actually having for shapes. This might take a second, by the way, for running, because we need to load all the files in the memory. This usually takes a few seconds. Now, what we do is we get out here 2 matrices. The first one is the element coordinates matrix, and the second one is the results vector for these elements. Okay, so this is a pretty neat function for extracting data, because the data in here is object oriented, and here for math computations, of course, we need matrices. Oh yeah, you see, this is the reason why you rarely should copy code at all, simply because you can do the same dumb stuff as I did, and you kind of may forget to change some important stuff in these functions, And yeah, then you get errors like this, that the name is not defined down here. I think it was also in a book which I've read that you should never copy code, but I'm just way too lazy for this. It's just my nature. Okay, here we popped up this print statements. In the first matrix of the first mesh, the element coordinates, as you can see, we have 52,888, oh man, that's complicated, elements. And here we have 53,000. And on the other way, here are the result vector shapes, so they're also incompatible. And now let's do the mapping operation. So this is just for demonstration. And let's map, I don't know, the second one onto the first one. I just, yeah, noted here. So first we need to import from sklearn one of the most awesome library features so far, the KD tree, which is called k-distance tree. And this is really, if you want to compute nearest neighbor distances, use a KD tree. It kind of like subdivides it's a distance tree, and it's made for fast computations. I don't want to get into the theory here too far. Okay, so here we go. We simply build a tree, and you kind of build it in such a way that you drop in the coordinates. We need to drop in the coordinates of the second mesh, which, yeah, we will want to translate onto the first. So don't get it, not the base mesh is inside here. And then we have to use the distance function. So here we go. We want to get the distances out of it. Maybe I will just make it bigger. Maybe this is better, hopefully. And we take the tree and we run a query. Don't know why it's called query. And we take the element coordinates of the first mesh, of the base mesh. I will explain in a second. So we want to get distances. We don't want to sort, because this takes time and we don't need it. And we want to use for neighbors. Now what we do is, this is exactly the same operation as I've shown you here. We kind of do now for each blue one, we find its 4 nearest neighbors. I do only 4 because it's a shell mesh mostly. So 4 should be fine. And I take the 4 neighbors, and what I get are the 4 distances. Okay. And I also get the mapping indexes. So kind of like where is this point in my data matrix LM chords 2? Okay. We will need this in a second. Now let's make this more clear. The distances, unfortunately, they're distances, and we need to normalize them. And what I usually use is I normalize them and I let them sum up to 1. So you have some really nice distance weights. And the way I'm doing this is called softmax. If you've ever been into sorry, if you have ever been into machine learning, they use softmax distances or softmax function quite frequently. And it is really no special function, okay? Because it just does what I just told you, that it just lets the weights between to be between 0 and 1, and you just let it sum up to 1. So here we kind of do like a exponential distance weight, and then thereafter we simply normalize it, and these are the distance weights. And yeah, maybe I should show you what shape we have here, like the distances. and the mapping indexes. They should have the same amount of shape as I've shown you before in the data matrices, but on the base mesh. So let's wait another trillion hours here. Just kidding. Of course, we don't have to wait a trillion hours. No, so far, if you don't know softmax, look it up. It's really useful. And as you can see, only need 2 lines. And I could make it 1 line, but I'm very oh man, how could I do this import wrong? I try to keep speed up here because these matrices might be large, and if I would just use this operation here and copy it in here twice, it would be a waste in my terms. Maybe not for others, but let's, I always keep an eye on performance. It's just a real problem because, these are the large matrices. Sometimes take a little bit of time. Here we go. So as you can see, it has the same shape, the distances, and also the mapping indexes as the base mesh length. And you have these 4 entries in both of them, like the 4 neighbor distances and the neighbor indexes. Now comes the magic function, okay? So let's call it FEM-Data2 on, I don't know, LM1. So we kind of perform here the mapping, and we do this weighted sum of the distances times LM-Data2. Okay, so this is kind of like we weight it, and now we have to apply the mapping indexes in here. Here we go. And for black magic, we also need to say that it has to do it line-wise. It's a little bit magic in here. If you know NumPy well, you will understand this one here. And what this simply does is for every element, it will compute these element-wise distance, value, whatever, and we'll sum them up. So this is exactly the step here. So at first we weight this one with this one with this, and so forth, and then we sum it up onto this one, and then we go to the next one, which might be here. Okay. And the cool thing is now I want to show you that we have the same shape. So what we wanted to do is we wanted to map out data 2 on data on the mesh 1, and no, we should use the shape here. Oh yeah, okay, that should work. So what you should see now is that these 2 matrices, or vectors better said, should have the same shape. Okay, I hope so they will, and I hope the program will not crash. But yeah, oh, this is tiny, but it should be fine. The mapping, or let's say moreover the loading and this extraction step usually takes some time. As you can see, the result vectors have the same shape. And now if you want to compute, for example, the difference between the 2 results, you can simply do subtraction or whatever, it's just possible. It's quite easy. Now this is a little bit abstract, so I did of course this for a very specific purpose. This is kind of like one of my test files from my PhD, and these are 3 simulation runs. And as you can see, there's a plastic strain, and all of them buckle differently. And what I want to do is now compute the scatter between these plastic strains or distributions, or let's say I want to see how much, where are the differences, the largest differences between all of those runs. So how did I do this? I will just put it on the other one. I wrote a second script. It should be in the same folder. Yeah, it's here. And oh yeah, I won't need this one here. Okay, this is all the code you need to see. Up here, I simply specified which results I want to analyze, like before. And here, I simply load the first file, and then I use the second this function here, which I've programmed just recently into my library, which is called compare scatter. And what it does is it loads these two files, maps it onto the first file, and computes the maximum scatter, like for every element, how large was the scatter in between. For the results which we chose here. This is the plastic strain. Maybe I will do a second one in a second one in a second. Okay, so this is everything. Let's run it. Here we go, darling. No, here we don't go. I think it was called compare scatter. It was the wrong one. Did I correct the main? No, I didn't. The second one, the second main, was simply for plotting purposes because it kind of made the plots which you just saw. Let me just bring up the second here. So when it will be finished, it will automatically open it the same way with this D3 plot HTML plotting function, which came in quite handy, I must say so. Okay, so what it does now is it is loading these three files, like I said, and it is computing for every element on the base mesh. It is mapping it over to itself, the results from the other mesh, and it does like maximum minus minimum in between all runs of the results at that point. And here we go. It just finished and it is loading, and here we go. This is the scatter, which looks reasonable because we have like a buckling here, and in one run buckling here. As you can see, chuck, 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 and chuck, chuck. These are more similar, maybe. Note that this is undeformed mesh everywhere. Usually this should be deformed. So this is kind of like the deformation. And by the way, I should have noted it. This is a plate which drops onto this model here. I totally forgot to mention. It must be very confusing watching only element results. So this is kind of like dropping here, and it is folding, and this is the scatter. As you can see here, the scatter here of the plastic strain is quite large. It's 126%, but here, for example, it's only 3%, and here it is only 1.2%, and so forth. So this is kind of like what the largest scatter looks like, but it's very reasonable. Now, we can also do the scatter maybe for the displacement, because today I'm in a good mood to do this. Here we go. Let's just comment this one here. We want to do the displacement. Load the displacement better said, and then we use the element coordinates, but we want to get the y displacement here. I will explain it in a second, because it will run another few seconds when I'm starting this. So here we go. What I'm now doing is I'm loading the displacements. Where the heck is my... here it is. I'm loading the displacements. Okay, and since this one here is falling down here and folding, you have a lot of displacement here in this area, but not here in the lower area. So what we should see is here some really high red scatter here, because sometimes it's falling here way down, and sometimes it's falling here way up. So this is quite a neat functionality in order to do the comparison here for the scatter. And here we go. Hopefully it will be correct. Here we go. So as you can see, we have some high displacement scatter here in this area, because sometimes the buckling is here and here, and yeah, therefore there is some difference in all of this. Yeah, that's everything I wanted to show you. I want to note one more thing. I know no tool so far on the market which can do this operation with these two commands here. And also mapping usually relies on commercial tools and everything, and I just want to emphasize here that do it yourself. It's not complicated, and the only problem in my sense was that people don't have these data matrices or data access. And I think with my library I want to provide this data access so you don't have to rely always on these commercial stuff, because this is really not complicated. And as you can see, mapping took just 5 lines of code in total, I think. Let me just look it up. It was, okay, 1, 2, 3, 4, yes, 5 lines of code. Maybe I could even squash it to 4. So, take it on, you know, take Python, do your thing, have fun, and release also your code, please, because it might help others. And yeah, only of course if you don't work in a company, otherwise they will fire you. Okay, so have a nice day.